Welcome back, everyone, to undergraduate seminar. Today we're going to hear about enumerative geometry, past, present, and future, from Gabriel. Thank you for coming and volunteering. I'm super glad to have you here. Gabriel, take it away.
Well, thanks for letting me speak. So I'll be speaking about enumerative geometry, past, present, and future. And my main goal today is just to give a grand tour of some of the history of this field, some work I've done, and point to some directions that enumerative geometry is going towards. So to start, enumerative geometry asks geometric questions of the form how many and expects some natural numbered answers. So let's look at some examples of this. Classically, Euclid posed the following. Given 2 points in the plane, how many lines pass through both points? And sometime later, about 100 years later, Apollonius, who was a mathematician from Anatolia in present-day Turkey, asked, given 3 circles in the plane, how many circles are tangent to all 3? And almost 2 millennia later, in the 1800s, Jakob Steiner asked, given 5 conic sections in the plane, how many conic sections are tangent to all 5? And we can see the similarities between these questions. So now let's turn to some answers. So probably have seen this in school at some point. So given 2 points in the plane, how many lines pass through both points? And there's one line. So we can draw this with 2 points in the plane and one line. And as with Apollonius's problem, given 3 circles in the plane, how many circles are tangent to all 3? And the answer is 8. And here's a very nice picture of the 3 shaded in circles, right? 1, 2, 3. 1, 2, 3. And we have all these 8 possible not shaded circles that are tangent to all 3. And then for Steiner's problem, given 5 conic sections in the plane, how many conic sections are tangent to all 5? And Steiner himself gave an incorrect proof, but this was later resolved by Chalet and Dejonrique in 1860, where given 5 conic sections in the plane, there are 3,264 conic sections tangent to all 5. So to unpack this a bit more, in this picture, we see 5 conic sections. So that is one being this hyperbola with 2 branches. So these 2 are ones. And then 2, 3, 4, 5. And then here we have one tangent conic that's illustrated in red. But the claim is that there are 3,263 other conics in red that satisfy this tangency condition. And it's perhaps surprising that there are well-defined answers that do not depend on the choice of points or circles or conics. In other words, under some mild assumptions, there's always one line passing through any 2 points. There are always 8 circles tangent to any given 3, and there are always 3,264 conics tangent to any given 5. And this surprising fact is what Hermann Schubert called the principle of conservation of number. And I'm being intentionally vague about what these mild assumptions are, but I will return to them later in the talk. So now let's think about the geometry of circles. So a circle in the plane is determined by 3 parameters, the 2 coordinates for its center and its radius. So we've probably seen this in pre-calculus at some point. If we have a circle with center AB and radius R, it can be defined as the vanishing of this polynomial equation. So, so we can thus think of the space of circles as some 3-dimensional space. So let's let this be the z coordinate, this be the a coordinate, this be the b coordinate. Then walking around in the upper half three-dimensional space, we trace out a family of circles. So right here at the origin, we have like the trivial circle centered at 0, 0 with radius 0. And then as we move out along this axis, say, right, we are getting circles of increasing radius. Sorry, this should be r. We get circles of increasing radius. And then as we move left and right, we shift around the center of the circle. So hopefully this is convincing enough that the space of circles, that there exists this space, the upper half three-dimensional space that parameterizes circles. Every circle is a point in this upper half three-dimensional space. And we'll come back to this later. So now let's look at answers to these enumerative problems that I posed earlier. So as I mentioned earlier, the answer to a how many question should be some finite natural number. And we want this answer to be nice in some sense. And what does it mean to be nice? An answer of 0 or infinity wouldn't be very satisfying. So we want some natural number, finite natural number as our answer. So let's consider Apollonius's problem as a case study. So the condition that a circle C is tangent to a given circle C prime is a one-dimensional constraint on the three-dimensional space that we saw earlier. So intuitionally, we can think of this as some plane in three-dimensional space. So fix a circle C prime. Every circle in this plane will be tangent to C prime at some point. And having a circle being simultaneously tangent to three circles, C1, C2, and C3, is having these three two-dimensional subspaces intersecting. And therefore, this intersection is a finite set. So we expect a finite number of circles that are tangent to all three. So what's really happening here is that these are three quadric cones intersecting. But thinking of them as planes is sufficient, right? If we go back to linear algebra, two planes intersect in a line, intersecting a third plane will get us down to a point, i.e. zero-dimensional set. So counting the number of intersection points of these three surfaces in 3 space, we get our answer of 8. So an analogous question one can ask is, given 3 conics in the plane, how many circles are tangent to all 3? So this is a variation of Apollonius's problem. And this was posed by Paul Breiding in 2018, who was one of the co-authors on this paper.
It's really surprising
So,
that it was posed in
sorry?
2018. Which is surprising that problem was posed in 2018 and not 1820.
Yes, that's true. I couldn't find any reference to anything earlier, but yeah. So here what we have is we have this number 1, we have a hyperbola of 2 branches and these 2 ellipses, and we have 1 red circle that's tangent to all 3. So what is the answer to this question? In 2005, Emrys and Zumas give a partial answer. Given 3 ellipses, they show that there are at most 184 circles tangent to all 3. And just last year, we strengthened this result that given 3 general conics in the plane, there are exactly 184 circles tangent to all 3. And unlike the proof of Euclid's theorem and Apollonius's theorem, the proof here requires some more advanced machinery and intersection theory. So I won't be going through the proof of it, but I hope the statement will suffice. Okay, so now it's time for a confession that the pictures I've drawn for you are all drawn over the real numbers, but all of the statements that I have previously featured are only true over the complex numbers, since these statements boil down to counting the number of solutions to some system of multivariate polynomials. That is, we need to work over an algebraically closed field, but R is not an algebraically closed field. We need an algebraically closed field. For example, a degree n polynomial over R need not have n roots. A famous example is x squared plus 1 equals to 0. This has no real roots. So an interesting question to ask is that what versions of the theorems that we have discussed before hold over the real numbers? And on one hand, these questions are of intrinsic mathematical interest, but on the other, these are closely tied to questions that are posed in applied mathematics, such as in robotics and physics, and I'll talk about this more later. Okay, so now let's think about so just to go over what I said, questions in real and enumerative geometry of interest. For example, it makes sense to tell a robot to move 2.1 meters forward. It doesn't make as much sense to say move 1.3 plus 2 to the I meters forward. So pictures are nice. I like pictures. So let's think about some problems in real geometry. And we can start with what we first started with, Euclid's theorem. So given 2 points in the real plane, how many real lines pass through both points? And the version of Apollonius's and Steiner's problem, given 3 real circles, how many real circles are tangent to all 3? And given 5 real conic sections, how many real conic sections are tangent to all 5? But unlike the case of over the complex numbers, the answers to these questions over the real numbers will be much more nuanced. So why is this so? Over the real numbers, we lose this invariance of number phenomena that I discussed earlier. We no longer have well-defined solutions, and these solutions appear in some range, such as how a quadratic polynomial over the real numbers can have either 0 or 2 real roots. But at least in the case of Euclid's theorem, we don't have to delve into this complexity. Given 2 points in the real plane, that's exactly 1 line passing through both. But in the case of Apollonius's problem, we start to see the problem of the loss of invariance of number. So Pedo, 1970, showed that given 3 real circles in the plane, there can be 0, 1, 2, 3, 4, 5, 6, or 8 real circles tangent to all 3. So I think the paper is called the missing number 7, and that is because the number of 7 circles cannot be attained. And for Steiner's problem over the real numbers, Ranga in 97 proved that there exists a configuration of 5 real conic sections in the real plane with 3,264 real conics that are tangent to all 5. And the proof is not constructive, but in a paper by Breiding, Sturmfels, and Sachs-Timmer in 2018, they give a constructive instance of 5 conics with 3,264 tangent conics. But this isn't done in the sense that what number of conics tangent to 5 conics can be attained? As in the case of Apollonius's problem, we had 0, 1, 2, 3, 4, 5, 6, and 8. Can someone give me a list of the number of conics that can be, the number of real conics that can be tangent to all 5? I don't know of a result that's in this vein, and a computational, and I have some remarks on this in the notes of my talk, which are on my website, which I probably should have mentioned at the start. I'll put it at the end. Okay.
Your website is linked on the seminar page. So
okay, yes. So see talk notes, website, and then go to talks, and then the notes are linked there. Okay, so returning to Breiding's question, given 3 real conics in the plane, how many circles are tangent to all 3? And how many of these tangent circles can be real? So the upper bound of the number of complex solutions is 184. And this gives an upper bound to the number of real solutions. But the question of, is this upper bound attained, is still, we still don't know the answer to that. So for example, in the case of Steiner's problem over the real numbers, they show that 3,264 is attained over the real numbers. 3,264 over the complex, 3,264 over the reals. But we weren't able to show that the complex upper bound is attained. Instead, we showed that there exists a configuration of 3 real conics with 136 real tangent circles. And in fact, we say something stronger, that for every even numbered between 0 and 136, there is a configuration of conics attaining that number of real tritangent circles. But this is incomplete because we don't know what happens between 136, the constructive instance over the real numbers that we have found, and 184, the upper bound over the complex numbers, which leads us to the following conjecture, that there are at most 136 real circles. Okay, so
what happened to the odd numbers?
Because you're defining conics with real coefficients, the solutions appear in complex conjugate pairs.
Oh, right, yeah, there'll be complex conjugate pairs.
So everything has to happen in some even difference.
Okay, cool.
Yep. Okay, so next natural question to ask. Okay, so here's a picture. We have these 3 blue hyperbolae and 136 red tritangent circles. And for example, this is like a family of circles which has extremely large radius. And it's not a coincidence that the conics are almost degenerate. This is actually a key part of the proof in the paper. Okay. So a next natural question to ask is, how can we classify these solutions? So if I throw you 3 conics, can you tell me how many real circles there will be? Okay, so a conic is determined by 6 coefficients. And since we're looking at 3 conics, we are looking at 18 coefficients that determine the configuration of 3 conics on the base. So given 3 conics as a vector defined, a vector of length 18, how many real circles are there that are tangent to all 3? And this is a pattern recognition problem. There is some pattern that arises in the 18 coefficients that tells us the number of real solutions. And at least to me and to the people who are working with me on this paper, this is a task primed for machine learning. So we in fact show that machine learning works for this task. That there is a machine learning model that, given a length 18 vector, can accurately tell me the number of real circles that will be tangent to the system of 3 conics that it defines. And it attains a classification accuracy of 95%. So this is the prediction plot. And as we can see, everything is almost always clustered on the diagonal. So the predictions are all quite accurate.
This is really fascinating. This is not where I expected the talk to go.
Okay, so sure, this is one example where we have this very interesting phenomena of machine learning working. But how generalizable is this? Did we get lucky, or can machine learning be used in geometry more broadly? So about a month ago at this point, got the referee's report for the paper back, and part of the referee's report reads, "I'm skeptical on the general feasibility of the machine learning approach for classification problems in real algebraic geometry. But this is rather a philosophical comment, and it is clear that the question by itself is interesting." Okay. So how else can we use machine learning in real geometry, or geometry more broadly? So one way we can use machine learning in geometry is for the discriminant. So we are familiar with this from the quadratic polynomial. So the discriminant is a subspace of dimension n-1 in the n-dimensional space of coefficients that tells us when the polynomial has a root of multiplicity. So for example, in ax squared plus bx plus c equals to 0, we have the discriminant b squared minus 4ac. And if this is 0, then we know that our polynomial has a double root. And its positivity and negativity distinguish between the real solution counts. So yeah, so we have already seen an example of this. And in forthcoming work with Anna Siegel, we show that we can learn the quadratic discriminant to b squared minus 4ac to high accuracy. And in some sense, learning the discriminant is equivalent to the solution classification task that I mentioned earlier. In the case of the solution, in the case of circles tangent to three conics, the discriminant is just a much more complicated polynomial, but it is still a polynomial. Okay, so I'm almost done here. So since antiquity, so to conclude, since antiquity, mathematicians have been interested in questions of enumerative geometry. So on the left, we have the 5 Platonic solids. So these are the solids where each side has is the same, where each face of the polyhedra is the same shape. And then on the left, we have a clay tablet from the Iraqi museum, which lists the computation of Pythagorean triples, i.e. the whole number solutions to a certain polynomial equation. And today we recognize how these classical questions are closely tied into domains that are not only of mathematical interest, but are also drawn from various applications. So computation can be used to solve systems that are arising in a wide range of mathematics and pure and applied mathematics. So this is a book by Somies and Wampler about numerical systems of polynomials and how they apply in engineering and science. The middle slide is a set of notes from, I believe, the 2020 Arizona Winter School on quadratic shovel T. This is an application of computation, geometry, and number theory. And then on the right, we have Seth Sullivan's book on algebraic statistics and how these problems in computational algebraic geometry are used in data science. And these connections have led to, have been enabled by a wide range of software. So computational commutative algebra and algebraic geometry in Macaulay 2, computational number theory and Sage Math, numerical algebraic geometry and homotopy continuation.jl, which is a Julia package. I used this extensively in the writing of this paper. Computational group theory, GAP, and many, many more examples. But looking to the future, this is only the beginning of the fruitful interaction between geometry and computation. So just to highlight some other work that's being done in the areas I've discussed before. Samir Agarwal, Tim Duff, Max Lieblich, Rekha Thomas, Paul Breiding, Felix Rydell, Alina Shehu, Angelica Torres, and many other people are working on the connections between algebraic geometry and computer vision. 1900, Hilbert first posed in his problem number 10 if there existed an algorithm to decide about integer solutions to polynomials with integer coefficients. And Matiasevich, building on work of Robinson, Davis, and Putnam, showed that no such algorithm exists. But more recent work of Bjorn Poonen attempts to treat this application in the setting of rings of algebraic integers. And in the last few years, Marie Brandenburg, Christian Haase, Ben Hollering, Irene Portakal, and Tran have been investigating the applications of geometry to auctions and game theory. But this is only a sampling of what's out there. There are so many more questions and connections for all of you to go out there and explore. And thank you. I'll take questions.
That was a wonderful talk. That was very, very nice. Questions from the room?
Yeah. So back to learning the discriminant for the quadratic equation. So
Yep.
how much was learned and how much was told to the computer right off the bat, right? So it has learned the number four. It has learned very close to number 4, but
Right. So the pipeline is built to learn the polynomials discriminants more generally by recovering it as the decision boundary of the Zariski open sets where the number of real roots are constant.
Right. So what? Oh, okay. So
what I mean, just to be more concrete about this, let's start with this is -1, -1. This is 1, 1 square box. And then what one can do is we can sample points all over this box and then label them by the number of real solutions. And then using some computational machinery, you can go back and you can recover the decision boundary of the machine learning model, which will be a curve, that looks something like this. And then here we have 2 real solutions, and this is 0 real solutions, if I'm remembering it correctly.
I mean this. The discriminant does not have an A² term. Did the computer find out on its own, or did you tell the computer upfront there's not going to be an A² term?
I did not, no.
cool. That's super duper neat. But yeah, it can kind of produce these. So like you're telling you've told it the answer will be a polynomial. And then
Yes, I've told it the answer will be a polynomial. I don't even tell it what degree the polynomial will be.
Okay, that's cool.
So not only has it learned 4 with high accuracy, it's learned 1 with high accuracy.
Yeah.
0 is probably other.
Yeah. That's what I was. Yeah, this is too good to be true. I have to ask.
Cool. I stepped out for a minute. Could you tell us a little bit more about the enumeration problem that you solved?
Right. So about here, or the general result or the result over the reals?
These 2 results. So, how do you actually go about finding these conics? With specific numbers of tangencies and this kind of thing.
Okay, so this was proven by computer. So the idea is that you can write an algorithm to increase the number of real solutions iteratively by using an optimization problem. And then you produce a file of, what is this? 136 over 2 is 63, 64. So you produce a file of 64 vectors of length 18, which one claims that correspond to the appropriate solution counts, and then you run it through a program and it uses symbolic methods to verify that those are actual solutions. And how you find this in the first place, the configuration of 136 was found by a geometric argument. And this is why the solutions, the three conics here look so degenerate, because it has to be almost degenerate. You start with a double line and then you deform it to a smooth conic. And then within one circle, a circle that's tangent to the line will split into two that are tangent to the conic, and then enumerating over all the possible splits and all the possible point and line conditions, you get the answer.
Right. So this configuration has some clever idea built into it. This wasn't. This requires some human creativity.
Yeah. Right.
The maximal one. Or
Yes. And then given the maximal one, you can you can see the search algorithm there and walk around in that neighborhood in the parameter space, generate more examples with high solution counts.
Cool. This is super duper cool. So yeah, you're doing more work on this machine learning AI stuff. So it's you and Anna Siegel. Are there other people doing this machine learning AI stuff? It seems
Sorry?
Are there more people doing this machine learning AI or machine learning algebraic geometry stuff and kind of computer search algebraic geometry stuff?
Well, not in the realm of enumerative geometry, as I'm aware, but there are a lot of people working in the connections between machine learning and algebraic geometry. Kathleen Cohn comes to mind, Guido Montufa, Marie Brandenburg, who I mentioned in the final slide. She does some work in this area also.
I had the impression that this computational thing went, even in enumerative geometry went back. I remember Arnold has a book on real algebraic geometry. And had some research in there.
Okay. But yeah, and then more recently there was the book by Satilli, I believe in 2010. Yeah, but yeah. No.
Cool. Other things you want to ask? This is a surprisingly low turnout for seminar. It's just the two of us in the room.
Oh, okay.
Yeah, usually we have, in the summer we'll have 5 people. In the semester we'll have a dozen. For Andy, our only online participant, I'll send the link. There. So Andy, if you're listening, if you could fill this out, be handy to get feedback to Gabriel.
What is this? What is this?
What's up?
What is this? Oh,
Oh, that's Gabriel's.
oh, okay.
It's Gabriel's telephone.
Yeah.
Cool. Well, thank you for giving this talk. It was really well done. I can tell that you also have an interest in classics. I thought the
Yes.
historical background was nice. Yeah, so thank you very much. We will have a seminar next week. You're definitely welcome to join us.
Yeah.
Yeah, this was lovely. I will post your video later this afternoon. If you can send me a copy of the slides, I'd appreciate that.
Oh, yeah.
But yeah, stellar talk and really, really interesting work. Thank you.
Thank you. And if either of you have any feedback, please feel free to share too.
Sure. We will. Have a good day,
Thank you.
everyone. Well.